I'm just going to hand the whole presentation over to him, talking about passive houses.
Pretty good,
Yeah?
thank you.
Okay, thank you.
So, Passive House is a German building design standard, and it was created to address climate change. So I graduated from the University of Massachusetts at Lowell with a degree in electrical engineering, designed integrated circuits for quite a long time, and then changed careers. I became a peak oil advocate back when we thought we might run out of oil sometime soon, but it soon turned out that we figured out that we were not going to run out of oil too soon, we were going to run out of oil too late, meaning we were going to burn too many fossil fuels. But the cure was the same, to reduce energy use, so I was working in a productive direction. I designed my first zero net energy house, and I'll explain what that is in a bit, back in 2008. After that, I went to take Passive House consultant training, 3 days of 3 days, 3 sessions of 3 days. And about 2 hours into the first session, I thought, these people are crazy. No one will ever go to these extents to build buildings. But I had paid for the first 3 days, and so I stayed. And at the end of the 3 days, I thought, well, this is worth pursuing. And I went through the rest of the program, became a Passive House consultant. And I have designed, verified, and certified several Passive House, many zero net energy possible homes, over a dozen deep energy retrofits of existing homes by reducing energy use 75% or more, and dozens of tier 3 homes, homes that I consider good enough to be a contribution to the solution in 2050 rather than the problem. When I design integrated circuits, you have to be very careful to get it right the first time. So I build a computer model of the integrated circuit, a test bench to drive stimulus into the circuit, and then a test bench to examine the outputs to make sure the functionality was correct, because after you send it off to the foundry to create an integrated circuit, your mistakes will literally be cast in stone, because silicon is a kind of stone, right? So you make all your mistakes in the test bench with software very, very quickly. You get it all perfect, then you send it off. And that is also the way we design passive houses. So this is where we live. And if you can imagine a sphere as tall as I am, 6 feet, right? How thick do you think the atmosphere that we live in is? 6-foot sphere. It's about 51 thousandths of an inch. We look up into the sky and we see blue and we think, oh, this goes on forever. We live in a very thin layer that surrounds the Earth. And what happens is this. In this very thin layer, we have an energy exchange. We have energy coming in from the sun, and then we have radiant transfer out. And it turns out that when you increase the carbon dioxide content of the atmosphere, it resists the migration of that energy back out. It acts as a kind of insulator. John Tyndall, an experimental physicist, verified this property of carbon dioxide a long time ago. That's the fundamental driving force for climate change. So what we're going to do is talk about the Passive House Building Performance Standard. It was created in 1988 expressly to address climate change. And we're going to talk about some energy language. I'm going to define some terms that we're going to use. We're going to talk about how much energy our buildings use today, because in 2050, 85% of the buildings that exist then exist today. So we're going to have a big problem to deal with. We've only got 15% to build to new Passive House standard. So there are a couple of Passive House standards, and we're going to take questions at the end. I'd like to dedicate this talk to Alexander von Humboldt. He was a German, and he lived for about 90 years, quite a long time. And he was someone who was called a polymath at a time when there was considerably less scientific knowledge in the world. He held most of it in his head, and he connected things together. He created the concept of nature, this interconnectedness. This affects this, affects this. And that was a remarkable achievement. He also wrote about climate change, human-induced climate change, in 1800 when he saw the rainforest being cut down in Brazil. He wrote that there was no good end going to come of this. 100 years after his birth, there was a celebration in New York City, a city he had never visited. 25,000 people saw a bronze bust unveiled in Central Park in New York City. The New York Times devoted all of the front page to the celebration. So they felt that he had contributed so much to civilization by his thinking and his perceptions that they decided to honor him in that way. So Jose has presented to me a number of questions. I'm just going to flick through them real quickly on the screen. These are all questions you have submitted. I'm going to try to answer all these questions during my presentation. We're going to come back to the slide at the end and see how I've done and take questions from the audience. So Wolfgang Feist is the creator of the Passive House Standard, and we'll talk about the story, but first we're going to define some energy language. A British thermal unit, a BTU, is the amount of heat necessary to raise 1 pound of water, that's about 2 cups, 1 degree Fahrenheit. It's like a wooden kitchen match burning. A kilowatt hour, which we consider to be electricity measurement, but is actually a measurement of any kind of energy, will light a 100-watt light bulb for 10 hours. 100 times 10 is 1,000. A kilo is 1,000. 1,000 watts, kilowatt. It can also raise almost 1.5 tons of water, 1 degree Fahrenheit. That's a lot of energy. And we get that for 20 or 30 cents a kilowatt hour and from our electric grid, not counting the impacts of climate change. So 1 kilowatt hour is 3,413 BTUs. 1 meter is 39.36 inches. We have a yardstick, we have a meter stick. They measure the same thing, they're just different ways of measuring it. So, back in the early 70s, the Arab states were angry about the United States' support for Israel. And they decided that they would punish the United States by restricting oil production. The Organization for Petroleum Exporting Countries got together and constrained the supply. The price went up, the supply went down. Oil that was $3 a barrel in 1973 became $30 a barrel in 1980. Imagine if our price of gasoline went from $2.50 to $25 a gallon. So this caused lines. People were required, if their last digit of their license plate was odd, they would only be permitted to go to the gas station on odd days. And they stood in line for long periods of time. And if the gas station ran out before they got there, too bad, you're out of luck. Go find another gas station. And oh, by the way, you can't go to the gas station tomorrow because you have the wrong license plate for that. So this upset a lot of people. And some of them started designing buildings thinking, I'm going to be warm in case we can't get enough oil to heat our buildings. So they experimented with these passive solar buildings. And the characteristics that describe them succinctly are mass and glass. Huge amounts of glass, taking in large amounts of sun, trying to store all that heat in water or concrete or salts. And this was a very difficult strategy to do correctly, although it can be done with careful engineering. There was another camp of people who were trying to do this with what was called super insulation. That is to say, let's make a container that's really, really good for the heat. And let's make some little windows and take a little bit of heat in, but that's all we need. This is a house in East Pepperell, Massachusetts. And it was probably William Shercliffe's favorite house because it was small and clever and simple and almost no additional cost to make. So William Shercliffe was a physicist. He worked at Harvard and he worked on some interesting things, one of which was stopping supersonic flights from flying over the United States because of the damage to the ozone layer. He also worked on the Manhattan Project to create the first atomic bomb. And Shercliffe also had an interest in these buildings, these experiments, these passive solar houses. So he published a number of books. He went around and saw these buildings and cataloged where they were, and he wrote about them from the perspective of a physicist. And here's a little drawing he had of a section of a wall where he has a foundation and then a 2x4 wall carrying the load from the building down to the foundation. and then a little gap where there's no wood, and then an interior wall. And so they filled this with cellulose, and it was insulation that it didn't have wood conducting heat all the way through it. And some little interesting detail on the rim joist. So clever, interesting little ideas. He documented these all in these books, and you could still find them on Amazon. So Shrewsbury took what he thought, what he understood from all of these books and all these different buildings, and he distilled it into a press release of about a dozen points. And the first one was his ideal house would have superb insulation, not just thick, but clever. As clever as a physicist could devise. The envelope is airtight. There is no provision for thermal mass, no big concrete, no glass, no large vats of water or salt. No extra large south-facing windows, just normal size and number, no conventional furnace, no distribution for heat. Because this building was super insulated, you release a little bit of heat and it goes everywhere as it should. No weird shape of the house, no weird architecture, no big added expense. The passive solar heating is modest because we're making a really good container for the heat. Room humidity remains 50% even in the winter. In the summer, the house stays cool automatically. These aren't wild fantasy claims. He's a physicist. He's describing something he thinks can be realized, and it could. So he called this a micro-load passive house. That was the name he gave for it. And then the price of oil went down, and people mostly forgot about this. A few people kept working on it. But then, in Germany, Wolfgang Feist, another physicist, was working on a problem of how we safely provide for the energy of the future. So he was looking at nuclear fusion. He said, nuclear fusion, 20 years away. That maybe more than 20 years away, maybe not have it. And so a colleague of his in China, Bo Adamson, was touring China, trying to figure out how the Chinese get by with so little energy because there are so many of them and so few trees to burn for heating and fuel. And Adamson came back and they started talking. They found this memo from this press release from Shrewsbury, and they said, well, you know, this might be it. We can maybe save the energy we need in the future by building better buildings. And that was the idea for Passive House, the whole purpose of which is to reduce CO2 emissions. So independent of Shrewsbury and Feist and Adamson, in Zurich, Switzerland, there was an entity called the 2000 Watt Society, and their interest was in studying this problem because they've known about climate change for a long time. And so what they were doing is taking the total amount of energy that they felt could safely be produced in the world and dividing it by the number of people. Each person gets the same amount of energy. It's completely and absolutely equitable. So they did all the math on this, and they said 2,000 watts, that's it. That's the level of energy that we can safely provide to each individual on the planet without getting us in trouble from climate change. And so as you can see in the United States, we're a bit over that. So if we were really to be sustainable, we would reduce our emissions by 5/6 for each of us. Just think about that for a minute. So when we generate electricity from fossil fuels, in this case we have a coal plant. I can kind of tell that because there's this long conveyor belt taking many tons of hour per coal and dropping it into the fired boiler, and that steam from the boiler turns an electric generator, and then we throw away about 2/3 of the heat energy in the coal using cooling towers or cooling with water. And this is a diagram by Lawrence Berkeley Livermore Labs that illustrates how we use energy in the United States. And what we're going to focus on is electricity. Electricity has these inputs on the left, including large amounts of coal and natural gas. And the inputs to this are 38.4 quadrillion BTUs, which is a really large number. And the useful electricity that comes out is about 12. So when we divide the amount coming in by the amount useful energy coming out, we find we have a primary energy factor or multiplier of 3. Now, why is this important? We pay for electricity at the electric meter at our house, right? That's what we see. We don't see what's in back of the meter. We don't see the 2/3 of the energy that we throw away. We just see the clean electricity. But there's a dirty story behind that clean electricity. So let's introduce the idea of a zero net energy house. So we shine sun on a photovoltaic array, and we have some electrical loads in the house, right? But if we have more electricity being produced than we're using inside the house, we export it and we run our electric meter backwards. So we build up credits, right? And then the sun goes down and we start pulling electricity from the grid and we run the meter forwards. So if the credits and debits balance out at the end of the year, if we produce the same amount that we consume in a year, the electric meter is in the same place at the 12 months later, we have a zero net energy house. And it's not at all difficult to make a house where the production exceeds the consumption. We have an energy plus house. I have a number of clients that produce enough surplus electricity to drive their electric cars for 10,000 miles. This isn't even that hard or expensive. We've done it a number of times. This is an illustration of a photovoltaic array producing electricity on a monthly basis, kilowatt hours, right, of electricity and months of the year, and then how much the house consumes. This is a very carefully designed house, so we're very careful about how we use the energy. What do you notice when you look at the energy that's produced and the months of the year? So what we see is that we're producing much more energy in the summertime, and that makes sense, right? Because the sun's up more hours in the summertime than it is in the winter. So that's pretty easy to understand, but look at consumption. We're consuming a lot more energy in the wintertime. Well, why is that? We're spending a lot of energy to heat the house, that's why. So these are out of balance, but this net metering idea allows you to use the grid as a lossless battery. You drive energy into the grid, run your credits up, and then deplete them, and at the end of the year, we have that accounting. So this is a tool that is online and free from National Renewable Energies Lab. It's called PV Watts. You put in your solar panels, what tilt they are, what direction they face, due south, southeast, southwest, or even east and west, and that can work. And it will print out the amount of energy on a per monthly basis that they produce. So it's a design tool, right? So if you can design your house for a certain amount of energy, you can size your PV array to balance that, or exceed it if you want. So, given the idea that Adamson and Feist had to try and address climate change in buildings, let's see if it stands up. We have the energy use in the US by sector. For transportation, we use quite a lot. Industry, manufacturing uses quite a lot. But residential and commercial buildings, that's 41% of the energy we use in this country. So maybe Feist is onto something. Maybe there's a big slice of the pie that we can attack and reduce the energy use. So let's take my house in Stowe, Massachusetts. I've constructed an energy model for it. I've done that for computer integrated circuits. And we're looking at, for example, the cooling energy. I don't need a lot. Hot water, not a lot. And lights and appliances. Now, passive house, we would attack all of these viciously, but here's the big piece of the pie. Let's go after that. 64% of the energy. If we could cut that down by 90%, that would make a big dent, wouldn't it? So let's break that down. How do we use heat? So we lose heat through the ceiling, through the rim joists, through the walls. These two are pretty big. Then we've got foundation losses. We could insulate the walls, the ceiling, the roof more. Doors are kind of a small slice of the pie, but we could do better with windows and we could do better with floors. What's this infiltration stuff? Insulation is the only thing that controls heat loss in homes, isn't it? That's not really true. In fact, about 1/3 of the heat loss in most of our homes is air. This is how that works. So this is snow on the ground, right? It's wintertime. These men have put up a scaffolding to work on the outside of the building. It's cold, so they've wrapped it in plastic. And they've put a propane heater in the bottom, right? So now this is a lot like a fireplace with a fire burning and a chimney, right? And so with the expanding air rising, it creates a negative pressure lower down, pushing the plastic against the scaffolding. And at the top, it pushes out above the neutral pressure plane. So this is how the stack effect works to move air through this construction, this scaffolding. And this also happens in houses. Air leaks in, down low, cold air comes in, it gets warmed up a little bit, and then it rises into the living space, and then your heating system heats it up even more and expands on top. So air comes in, cold air comes, and warm air comes out. Cold air comes in, it creates a loop, a convection loop, and a convection loop pumps heat out of the house, and that's a third of your energy bill, I'd say. Pretty interesting. So if we can air seal these, if we can prevent that air from coming in and leaking out, we can save a lot of energy. But everybody thinks about insulation, not air sealing. So how do we measure this air infiltration thing? We do it with a blower door. This is a metal frame that fits in a doorway with a fabric, and we put a big fan in here, and we have this airflow computer, which I'll expand, that measures air pressure inside to out and the amount of air going through the fan. If we look at this in the context of the house, here is the blower door frame. It's exhausting air from the house, remember that, so air is leaking in everywhere. There's no air going out at the top. All the air is leaking in, coming into the house and being blown out. We measure that at a pressure of 50 pascals, the standard test pressure. If you try to do the measurement the next day, it's within 10% accuracy. We can calculate the heat loss from that house pretty effectively with this number. So when we built our first passive house in Falmouth, Massachusetts, we were very concerned about meeting the air tightness criteria, which I haven't shown you yet, but it's very, very strict. So we put a blower door in here with a tiny little fan because we were measuring a tiny amount of air infiltration. We tested the building first before we put the windows in because we thought, wow, if we put the windows in, we won't know where the air leaks are so easily. And in fact, we did pass the very first time. We got a very good number without the windows. But when we put the windows in, they leaked. So there's the idea of when it's colder outside, when you use a blower door, you're evacuating air from the building. So wherever it leaks in, and there's a picture of the clip here, the air in this infrared picture is cooling off the surface. And so in an infrared picture, darker temperatures, darker colors represent lower temperatures. So we can see this thermal signature that you can't see with the naked eye. So we can see this from across the room, go up, feel it with a hand, say, there's an air leak, and we'll fix it. So that's how we fix the problems in the air sealing of the windows. So now back to existing buildings for a moment, 85% of which we have in 2050 that exist today. We're not going to tear down all our houses and build them. We're going to keep them and we're going to have to deal with them. So let's look at how we can account for energy use in existing buildings. So site energy, again, this is not the primary energy, this is the energy you see at your electric meters. If you take your electric meter and your gas meter and your oil going in, and wood and all that, convert it all to BTUs. And then we have a certain number of square feet of area in the building. If we take the BTUs we use in the whole house, divide it by the number of square feet, we have something called energy intensity. Per square foot of living space, how much energy we use. So we can compare houses of different size. We've got this metric that's pretty good at comparing that. And so when my business associate, Paul Camp, graphed these thousands of BTUs per square foot per year for 120 houses, he found that at 70,000 BTUs per square feet, 60 of the houses use more, 60 of the houses use less. So if we build a really nice zero net energy home with good insulation and air sealing and windows and all those things, it might use 35,000 BTUs per square foot. We say, wow, we cut that in half. That's really something. A passive house uses 1/3 of a zero net energies house. So that's a remarkable reduction. You notice it's not 38, it's 12. We're talking about site energy. We're dividing that 38,000 by 3. So we're talking apples to apples comparison. So how on earth do you do this? So the passive house criteria, and this is a picture of a passive house I designed in Westport, Massachusetts. So we have some very rigid numbers that you have to meet. You have to meet 4.75 thousand BTUs per square foot per year for heating only. And that is about 1/10 of what our houses use. Same number for cooling. The primary energy, that is the controlling factor that means that you can't use any more than that, therefore you can't produce any more CO2 in using that energy. Then we want a very airtight building. 0.6 air changes an hour at 50 pascals. That's about 5 times tighter than the current building code, 10 or more times tighter than our existing homes. Because the building is so airtight, we need to bring in ventilation air, and we do about 3 air changes an hour, about 1/3 an air change an hour for ventilation air. There is a comfort criteria because we want to be comfortable in our buildings, right? And so if you have a 68-degree room temperature, you subtract 4 degrees, everything including the windows cannot be below 64 degrees. That's very difficult to do with windows, but it is possible. And then this is certified by a third party. You can't just claim it's a passive house. You can't just say, it is a passive house because I say so. A third party has to certify it and describe that. So the tool that is used, the software tool that is used, turns out to be a spreadsheet. When Wolfgang Feist designed the first passive house, he used supercomputers that he had available in Darmstadt, Germany to design it. But he realized that not everyone has a supercomputer. This is 30 years ago. So he created a spreadsheet that you can use based on those formulas determined by the supercomputer simulations that cost $200. And you can buy one of these things and calculate your space heat demand and space cooling demand and primary energy. And that is how we determine those numbers. It's a calculated value. So now we're going to turn to ventilation, which is something that is unfamiliar to many of us. And I'm going to describe to you a situation in the house I own. My house leaks a lot of air. I bought it that way, and it's hard to fix that after the fact. So it's 5 air changes an hour, and I go into the bedroom at 11:15, I close the door, and I'm looking at carbon dioxide in parts per million versus the time of the day. I've got here a device that is measuring carbon dioxide, and we're up to about 11,000 parts per million right now. It's gone up from, what, I think 600 this morning because we're breathing in and out of this room. It's getting some ventilation. So the next thing that happens is that I turn on a bath fan that's across the hallway, and that changes things a little bit, but really doesn't do much to change the air in the bedroom with the door closed. Finally, I turn the bathroom fan off, and I open the door to the bedroom. And that's what really makes a difference, right? Because the carbon dioxide escapes and is changed with air in the rest of the house. So, is this 2,000 parts per million CO2, is that a big deal? Is that important? We've measured houses with 2,500 or 3,000 parts per million in the bedrooms overnight. And arguably it does. This is a study done by Lawrence Berkeley Livermore Labs, and it relates the impact of CO2 on human decision-making performance. So we have these symbols. We have white for 600 parts per million, blue for 1,000, black for 2,500. And you can see for some things like focused activity, it doesn't seem to make a lot of difference. And for other things like basic activity and, let's see, task orientation and perhaps information utilization, it does make a big difference. And United Technologies employs a lot of engineers to do what? Anything important? Well, they work on things like fuel systems and control systems for aircraft and designs for these things. Would you like their brains to be functioning well? You know, certainly yes. So United Technologies has picked up, they picked this up as a publicity thing, right? They are ventilating their buildings very well now because of this study. And there's also one study I know of done on college dormitories, which indicates that people get a more restful sleep when they have less CO2 in the room. You've heard the expression, a breath of fresh air. It has actual meaning to us physiologically. So we are just going to say, how about keeping the CO2 as a proxy for indoor air quality? If we can easily measure CO2, this is only $250. Let's say our goal is 1,100 parts per million, which just happens to be what's in this room right now. If we can ventilate and keep it at that rate, let's just call that good enough, because we need something we can measure so we can determine whether we are succeeding or not. So good enough for now. Actually, another German, Pettenkoffer, set the limit at 1,000 about almost 100 years ago, more than 100 years ago. Another story. So how are we going to change the air? If we change a lot of air, if we do 3 air changes one air change every 3 hours, that's a lot of cold air to bring into the house. That's going to cause our heating bill to go up. Well, not if we use a heat recovery ventilator, and this is how that works. From outside, we have this airtight envelope. We're going to bring air in one place. And oh, by the way, if we're bringing air in only one place, we could put a filter in there. We could filter out pollen, particulate contamination. The air in a house can be much cleaner than the air outside. For people with allergies, this is a real blessing. So we're bringing fresh cold air into our heat exchange core. And then we are exhausting stale air from the building. The heat exchange core takes the heat from the stale air and transfers it to the fresh air without mixing those two air streams. And so it warms the fresh air, recovers much of the energy, and we send out cold air. So we're looping back the heat, but not looping back the contaminated air. And here is one of those machines with the ports going outside. The outside ports and the indoor ports go to some little registers we put, and we measure and adjust the airflow so we have just the right amount of fresh air going into our bedrooms. And this is how it works. We have the air that's leaving the house, going outdoors, and we have a cross-flow path. The paths of air are going opposite directions. So the heat transfer is always from warmer to cooler, so we'll never get the supply air exactly up to the temperature here. But by arranging it in this method, even the cold air here is still transferring some heat to the colder air coming in here. So using these temperatures, we can calculate that we have a 90% recovery efficiency. And these machines exist even up to 95%. So it is possible to recover a lot of heat from the air and still get lots and lots of fresh air into the buildings. So let us put one of these heat recovery ventilators in a little bedroom. Let's put 2 people in there and and we see that this is 10 nights of data. So when they close the door, the CO2 concentration goes up. When they open the door, it goes down. We can see we're doing a pretty good job of staying pretty near 1,100 parts per million. That we consider to be a success. So we have measured data here done the same way. So a question for you. How do you think thermal comfort, being warm enough, is best delivered in homes? Can that be by a powerful heating and cooling mechanicals that we need to create that comfort, or the absence of powerful heating and cooling mechanicals? I'm going to argue that the second one is the real answer. So one of the people in my Passive House Consultants training, Jamie Wolf, created this diagram to illustrate the difference between conventional buildings and very low energy super insulated buildings. So we saw air infiltration coming in and leaving. That's a defect that we know is in our existing buildings. A super insulated building has an airtight layer we outline in red. Very little or no air gets through that. We have poor windows. By poor windows, I mean they don't resist heat flow very well. So warm air hits the top of the glass, gets cooler and cooler, and it slides down, just like stack effect in reverse. Finally, at the bottom of this window, we might see some little moisture. The reason is that the air gets colder and colder and colder until it reaches dew point, and the condensation happens from the water vapor. Conversely, in a superinsulated building, we might have R5 windows, or we might have R9 windows, or R11 windows, and these are affordable when you have the technology and technique to make them. So we have infrared exchange. All bodies that have temperature emit infrared radiation, and if the surfaces around us are lower temperature than our bodies, we emit more infrared radiation toward that. That's why the comfort criteria is so important, because by making sure all the inside surfaces are nice and warm, we are much more comfortable at lower temperatures. So another person in my Passive House Consultant training, J.B. Clancy, drew this schematic house to illustrate the key aspects of Passive House. We have an airtight layer outlined in red all the way around. We have complete insulation wrapped around the living space. We have the heat recovery ventilator I mentioned, changing the air. And we have, with the superinsulated envelope, a person, the heat we give off, we're 300 BTUs, each one of us in this room, roughly, emitting heat. And then we need a little bit more energy to get in here to heat. So we will create an overhang that excludes the sun when it's high in the sky in the winter, but allows it to come in the summer, and allows it to come in the winter when we want the heat. It's a little more complicated than that, but let's just take that for a moment. And we have this odd thing here. What does that mean? That's a thermal bridge. So if you think about this, we have a heavy roof, we have a building, we support that building on a foundation. Insulation is soft, squishy stuff. How do we keep from creating a thermal bridge here by creating something that's not insulation? So I'm going to first talk about what a thermal bridge is. We have a section, if I just slice this wall open and look down it vertically, there's a 2x6 framing member in a wall, and we have closed cell foam. We have 5.5 inches, because that's the dimension of a 2x6. And if we multiply 5.5 by R6 per inch insulation, we have R33 thermal resistance through the cavity. We have our exterior sheathing. This is drywall. This is the inside, 68 degrees inside, 0 degrees outside. Therm is a two-dimensional heat transfer simulator. I've built this wall, I've established the boundary conditions of 68 and 0, and I've turned on heat flux vector display. Heat flux vectors show the magnitude and direction of heat flow. Small arrows mean less heat flow, big arrows mean more. And you can see the heat gathering toward this 2x6 and going through it, right? So it's pretty obvious that we're bypassing the insulation. And this tells us how much. It calculates a U factor, so that means this wall is actually more like R27 than 33. But we don't just have framing members like this. We have top plates and bottom plates. We have framing around windows. 23% of our walls are wood like this when you design a building like that. So what that does is it reduces the actual real R value of the entire assembly to about R21. So that did a lot of damage to our closed cell insulation. And this is an illustration using color to show how much heat flux is escaping. So let's look at the idea of creating a bearing wall with 2x4s on the outside that carries a load down into the foundation of the earth. And then we separate this, we make a separate wall on the inside. We fill this cavity with let's say, cellulose insulation. We separate the concrete in the interior from the concrete in the exterior with insulation, so we create an unbroken thermal bridge-free construction that I showed you in the diagram earlier. And so if we run therm on this, we can see the little heat flux vectors are all trying to escape to the outside because the Earth is a little warmer than it is on a cold winter day. So this is the area where we most need the insulation. We might not need any insulation on a big building 20 or 30 feet away because the Earth is pretty warm. So if you think about a house like a bucket and think about the idea that heat leaks out of the buildings like water leaks out of the bucket, and we need a powerful heating system to put heat into the building, that seems like an odd thing to do for a building that will be there for 50 to 100 years because we keep pouring water in, heat in, year after year after year. Let's think about the idea of taking the heat leaks and covering them all up. This is the idea of a passive house. Spend more money, patch up all these leaks, and then you get a building that's good for 50 or 100 years with 1/10 the heating energy use, which as we saw is a major energy consumption. So passive houses do occasionally need a little heat. Not always, but sometimes. So the way we choose to do that is with what is called an air source heat pump. So we have an outdoor unit. There's a fan that runs air through it, heat exchanger, and this machine can extract heat from outdoor air that's 15, 20 degrees below zero. And you say, that's incredible. How can that possibly be true? But you all have a heat pump in your house. It's called your refrigerator. There's a compartment in your refrigerator called a freezer, and it is kept at 0 degrees Fahrenheit. all the time, 365 days a year, no problem. So the Japanese have figured out how to do this, and it works really, really well. In fact, it works so well that there's a line set carrying refrigerant, and that brings the heat up to the indoor unit where we have return air coming in and supply air being supplied at an elevated temperature. And this works so well because we're not using electricity as resistance heating. We're not converting it directly to heat. We're using it to pump heat from outdoors to indoors. We can pump 3 times as much heat out of the outdoors into the house as the electricity, 1 unit of electricity that we put into it. So that counteracts our primary energy factor of 3. So we can heat efficiently and effectively. And oh, by the way, we can also do excellent cooling and dehumidification because these machines are so efficient. So there are 2 certifiers of passive houses in the United States, Passive House Institute US, and then Passive House Institute Germany for the rest of the world. Pre-certification, before we build a building, what we do is we carefully document what it is we're going to build exactly in schematics. We choose the mechanicals, we obtain their specifications, we put it all together in a package, we pay Passive House Institute USA some money and say, look this design over. We'd like to pre-certify it before we start construction. They will find some problems. They will go back and forth with you and question and answers. We'll make changes. Finally, they'll say, okay, if you build this building exactly as we now have it defined, you can be assured of certification if you pass some additional tests. So, if you build it exactly according to the pre-certified schematics and plans, and you can pass some tests, the building should be certifiable. If you change the plan after it's pre-certified, you put yourself at risk. You can go back and ask them, is this change okay? And they'll look at it and they'll say maybe yes or maybe no. So, finally the house is built. Now, have we documented all the construction properly? Do we have photographs showing how much and the quality of insulation we did? We have to pass that 0.6 air change an hour blower door test. We have to verify the ventilation has been commissioned so it gives enough clean, fresh air to all the bedrooms. And then the construction supervisor signs a document that says this building has been constructed exactly according to the pre-certification documents, or exactly according to the pre-certification documents with these deviations. And so the deviations get looked at by the certifying entity, FIAS, and then if it's okay, it'll pass, and if it's not, well, maybe you fail until you can fix those deviations somehow. So it's a carefully designed process to assure quality. So that's for new house. Remember, we've got 85% of the buildings in 2050 in the ground today. This is a house that I worked on. We did a deep energy retrofit. We reduced the energy use by more than 75%. We did that by adding insulation on the outside. We have R9 windows in here, nice European windows. We did a number of things for air sealing and other things. And then he put 9 kilowatts of PV on the roof. This is a pretty big array. And this house is net zero energy. In fact, it's slightly energy positive. It's about 300 or 400 kilowatt hours a year positive, which is about 1,000 miles worth of driving in an electric car. This is a Falmouth passive house, the first one I designed and certified. And this is some temperature data that I recorded with these little data loggers. We have in blue the outdoor temperature, and you can see it gets as low as 10 degrees Fahrenheit. This is January of 2012, and this is Fahrenheit temperature. So it gets pretty cold out, and you see these pretty interesting oscillations in temperature. And one might guess correctly that that's due to the sun coming in, warming the building up, and the sun sets and it cools down. So let's put some temperature bars in there. Let's say our ideal comfort zone is between 68 degrees and 78 degrees. No, by the way, the owner was perfectly happy with this. He turned the heating system off. That's why the temperature is going up and down. If the heating system had been on, it would have been stayed at one level. So there's a little bit more fluctuation here, and it's getting a bit warm on some days. But the reason for these oscillations was this building didn't have much thermal mass. So when I designed my next building, I learned from this. Not a bad thing altogether, really. The owner never complained, but not ideal. So when we use lots of insulation, we have to be careful about what it is we're doing. And when you create anything, you manufacture it, you do material extraction, you use energy to process it. All of those things cause energy to be used, therefore CO2 to be emitted, so it's called embodied energy. And for cellulose, it's just chopped up used newspapers, very little investment in energy there, fiberglass a little bit more. In EPS, we have some plastic we're manufacturing, but that's not bad. XPS, the blue board or pink board you might have seen around, that has a gas that has very serious greenhouse gas warming potential, like 2,000 times carbon dioxide. Polyiso, on the other hand, the foil board, rigid foam board, that's not bad at all. Not as good as cellulose, but not nearly as bad as XPS. Closed cell spray foam is bad news. That's about 1,700 times carbon dioxide equivalents. So we have to be very careful. Generally, we design passive houses with these because we are being mindful of the problem with global warming. This is Secretary of Energy and Environmental Affairs Matthew Beaton's house. My colleague was designing this at the same time I was designing the Falmouth Passive House. This house is in Shrewsbury. This is the first certified passive house in Rhode Island. It was an experienced passive house team. Steve Basic was the architect, and Dan Roy, the passive house consultant, and Steve Demetric was a cabinet maker, so used to precision. Their goal was to design a house that passed passive house certification and was low cost. And this house is very nearly the price of the houses that are around it in a very modest neighborhood. We have a great room downstairs where we have kitchen area, dining, and living space, all nicely heated by the south-facing glass, 2 bedrooms upstairs, and a master suite in the back. All done for $163 per square foot. So I've been to 6 international passive house conferences in Germany and Austria. My wife's mother is from Switzerland. She has a friend, Martha Goering. This is where Martha lives in Switzerland. I fly into Zurich, jump on the electric train, and at her house in about 45 minutes. So her house is built to the Swiss Minergie-like passive house standard. You'll notice it's off at an angle to the road. That's because it's facing due south. She wants to take maximum advantage of south-facing sun, both for her 5 kilowatt PV that makes her energy positive, and for easy control of sunlight through the windows. This is a Westport passive house that I designed. We're going to use it to illustrate an improvement over the Falmouth passive house. What we have here in yellow is the outdoor temperature. It gets as low as -5 degrees Fahrenheit. And the indoor temperature. You can notice we don't have wild fluctuations here. This is recorded data. We're holding pretty well between 60 and maybe 70 degrees. So this is because it has a slab the sun shines on. That's a worthwhile improvement. And this is so comfortable that the owner has not turned the heating system on in 3 years. He and his wife are over 65, so they're more sensitive to temperature. And they're very comfortable because of the super insulation keeping the walls around them so warm. So 0 heating. So this is a 100% reduction in space heating load. You can't do a lot better than that. This is a passive house I worked on in Wayland, Massachusetts that has been certified. This is the first certified multifamily passive house in New Hampshire, Guilford Village Knolls near Laconia on Lake Winnipesaukee. It's 24 units of senior housing for low income, and we had received certification for this in December. Uses PV. It's not quite 0 net energy, but close. This is a small concrete building that was retrofit to the passive house standard in Newton, Massachusetts. It's the Center for High Performance Design and Construction. We just got certification for this. In fact, someone gave me the certificate just last week. So FIAS has certified this after we passed all the tests, ran all the calculations. It's a certified passive house. So that is the end of the presentation. Let's go to the questions and see how I did. My interest in Passive House is primarily in global warming, but also because it's an interesting engineering challenge. We've talked about the requirements, the pluses and minuses. It's harder to get people to change, to do something that's unusual. And certainly we have unusual assemblies, different insulating techniques, and so forth. The materials are different because we're looking for low energy. We did all our iterations in software, so we didn't make any mistakes when we built it. I think I've described that. It took about a year to design the Secretary's house, and it takes some time and patience to do this. Heating, we don't have much of a problem heating. And solar I've described. So I think, are we out of time, or do you have time for questions? Unfortunately, I'm sorry. Welcome. Welcome.